Hello and welcome to the first video of the class. We will start in chapter 1, which deals with atoms and elements. We will talk about all of these sections, and there's going to be videos for you to watch for all of these sections, but there's going to be only 4 videos, so some of these are going to be combined into one video. We will first talk about the study of chemistry and atoms first, and this will be in this video, and then the subsequent videos will cover the last 5 of the headings here. Well, first of all, what is chemistry and why is it important? Chemistry is the study of matter and of the changes that matter undergoes. Matter is all around us. It's anything that has space, occupies space and has mass. Everything around us, including ourselves, is matter. And so therefore, it's important for us to study and observe the changes that matter undergoes. We use chemistry all the time during our everyday life. We just don't think about it. We don't think in terms of chemistry, but everything we do, everything we carry, the food we eat, our own body is made of chemicals. And those chemicals undergo many changes, chemical reactions, and it's important for us to know some of these because that affects our life. Mass, then, is a measure of the amount of matter that is contained in an object. This is different than weight. Weight is actually a force, whereas mass only measures how much matter is contained in a three-dimensional object. And all matter has some mass associated with it, no matter how small it is, as we will find out when we talk about atoms. We study chemistry and any science using the scientific method. And most of you who have taken a science class before will have covered what the scientific method is, so I will not spend a whole lot of time talking about it. But the scientific method gives scientists a standardized way, if you will, to look at the world and conduct their experiments and come up with data and interpretation of that data. This is done to minimize the amount of bias, albeit know that we can never eliminate all bias because we are human beings and biasness is kind of woven into our nature, but we could try to eliminate it, and that's what the scientific method tries to do. The first step, of course, is observations. We look at the nature and things around us and we observe different phenomena and we get curious. And that is the first step because that's where it begins. We have to be curious about a phenomenon that we're observing, we're watching, and then we can talk about conducting experiments based on what we observed to try to explain something that caught our attention. Now, if we look at something, our observations, and we notice certain patterns, we can formulate a law that can encompass these observed patterns, and it gives us a mathematical relationship. So a law is just a concise statement of an observed pattern, or it can be a lot of times is expressed in a mathematical relationship. Not always, but a lot of the time. After we establish these observations and maybe laws, then we seek a hypothesis. We formulate a hypothesis. This is an idea, a guess, if you will, although we call it educated guess. but it is an attempt to try to explain these observations and why they are happening the way they are. Why are these patterns or these laws that we observe around us the way they are? This is what the hypothesis tries to do. And we do that, we try to establish the veracity of our hypothesis by conducting experiments to try to prove it or disprove it. If our experiments prove that the hypothesis is correct, then we gain some information from the data, and then we move on to a new question. Being in graduate school, we talked about hypotheses a lot, and a good hypothesis is one that will generate more questions than it tries to answer. And so this is a continuing process. We're constantly in science coming up with new hypotheses, new observations, new data, new experiments, revising old hypotheses, etc., etc. Now, if a hypothesis has withstood the test of time and experiment over and over and over again, so it's been subjected to a lot of scrutiny and experimentation, and it has withstood all that, then it can be expanded into more of a model or a theory that encompasses several laws and several observations. So it's a hypothesis that has been confirmed by multiple experience. It explains past behavior and tries to predict future behavior. Now there's a difference between law and theory. Theory seeks to explain why we observe what we observe, the reason behind it, whereas law doesn't tell us any of that. It's just an observed pattern or a mathematical relationship. So these two are different. This is a pattern that is used by all scientists in all over the world. And it just gives us, like I said earlier, a standardized way in which we can conduct experiments and minimize that human bias and human error. Now let's direct our focus to atoms and elements. Some definitions first. We will start with element. So an element is a substance that we cannot break down any further into a simpler form. For example, if I have a bar of gold, or a sodium metal, or aluminum foil, or a helium balloon, I can reduce the amount of each of those by dividing it into smaller parts and pieces, but I cannot change it into a simpler form. So if I have a helium balloon, that is filled with all helium atoms and nothing else. So in that sample, all of those atoms are helium atoms of that particular element and nothing else. If I have a bar of gold, that is only made of gold atoms and the element of gold. So if I'm talking of a substance, for example, like water, we all know that water is made of hydrogen and oxygen. So there are two elements, and I can then take that water and split it into a simpler form of hydrogen and water, two different elements. Whereas once I do that, once I split the water into a simpler form, into the elements that make up that substance, I cannot take hydrogen atoms anymore and convert them into a simpler form, or oxygen atoms. An atom, on the other hand, then, is the smallest quantity of matter that retains the property of that matter. So I can take the sample of helium and I can divide it into smaller and smaller samples until I reach a point where if I divide any further, then it is not a helium atom anymore or element. In fact, I have divided it into smaller particles, which we call subatomic particles, but they are not helium any longer. They're just particles. So an atom is the smallest quantity of matter that still retains the properties of that matter. So here's a picture of a bunch of USB flash drives. So if I take, this symbolizes a type of atom like the helium atoms. And if I take this and divide it in half, I have fewer, but I still have those flash drives or helium atoms. If I take them and divide them even further, I still have helium atoms or flash drives. There comes a point in time where I only have one left, and if I divide this any further, it is not a USB drive any longer, or it is not a helium atom any longer, and we destroy the atom. Now, the word atom was formulated back in the 5th century by a Greek scientist and philosopher. So the word and the idea has been around for a long time, but in the early 1800s, Dalton was the one who kind of formulated an overall theory and put all these pieces together into a more general theory of atomic theory is what we call it. Now, here's the three main parts of what the theory is. So matter is composed of these indivisible little particles called atoms. These atoms, as we said in the previous slides, cannot be divided any further. That's why it's called indivisible. Now, without destroying that element. All atoms of a given element are identical. So if I have a sample of that helium in a balloon, all of those helium atoms are the same. They're all helium and they're the same. They're identical. Atoms of one element are different from atoms of another element. That is what makes them unique. So if I look at the bar of gold versus the helium balloon, those helium atoms are different than the gold atoms. They're not the same, and they're distinct. Now we know that the atoms are divisible, and we call those subatomic particles for smaller than atom particles. But once we divide the atom, we do not retain the identity of that element, because once we divide the atom, they become those subatomic particles of helium are indistinguishable from the subatomic particles of gold or of carbon or any of the other elements in the periodic table. Before we get into the actual parts of the atom and these subatomic particles, let's cover a little bit of a review on electric charge. We know about electric charges because we have experienced it, and we can have an object that is charged, can have a positive charge or a negative charge. And then we can have uncharged objects which do not have a charge, an overall charge, if you will. We also know from experience that objects with opposite charges attract each other. So if I have a positive charge, it will be attractive to a negative charge. From experience, we also know that objects that have like charges they're not attracted to each other. In fact, they repel each other. This could be two positive charges or two negative charges. If they're the same, they will push away from each other. They will repel. If I have an object that it's got higher charges than another, basically this one has only one positive charge, this has three positive charges, so it's stronger, the charge is stronger here. The repulsion between these two charges is larger than between just one positive charge apiece. So we have stronger repulsion in objects that have larger charges than those with lower charges. Now this is true with positive or negative charges. Something else that is true is the strength of the charge. So if I have a, a charge, two charged objects that are closer to each other, so the distance between these two objects is shorter than or smaller than this one, these will repel each other much stronger than these. When we have opposite charges, positive charge added to a negative charge, they will cancel each other. So +1 minus 1 gives me an overall charge of 0. So even though I have a positive and a negative charge, together they cancel each other. So I have what is called no net charge, no overall charge. These principles are important in chemistry, and we will be building upon these. So it is important that you understand how charges behave, what happens when we have positive and negative charges, how they add up, and how they cancel each other, etc., etc. So to strengthen this idea and to give you some practice, here is a sample problem. We say that opposite charges cancel each other. So if I have these sets of data, A through D, which of these show cancel charges? And if the charges do not cancel, what is the leftover charge? What is the net charge then, once I add these charges up? This is the short little quiz that you have to do before you come to class. We will continue with part 2 in the next section.